Yeah, sure.
Well, the first recording says that it's temporary. Will this record will be temporary too?
It is not temporary.
Well,
It is temporarily available, right? These are two different concepts. You can download it right now,
okay,
but
okay, okay.
yeah, but I'm gonna create. I plan to have a like the OneDrive again, like last time I did,
Hmm.
and then upload all the videos there so you can watch them. Actually, the other thing is like I already have this OneDrive there. Let me open this thing up. These are the same stuff, same classes I do this like online lecturing in 2021, 2 years ago. So everything's almost same. Maybe I can just share everything with you, but let's find it. Okay, it is there. Okay, everything is here. So let me just share this thing with you. Stop sharing, share Windows. Okay, so these are from the 2001, and you can see all of this stuff is here. I can do the same stuff here, same stuff like that, and I can share this thing with you. But the thing is, I might remove some stuff and add some more stuff to there, so that if I share this thing like you, if I share this list with you right now, and you may not follow what I'm gonna say next, so that you just follow these lectures, and then you'll miss what we saw actually in the class. But I plan to do the have same thing with your lecture as well. I downloaded the video from the last week, and I uploaded like this, like week introduction. But today it will be new, and you can reach those videos. Okay, guys.
Thank you, sir.
Is there another question that you are saying this? Okay, guys. We're gonna discuss the regular languages this week, and the name of the class is formal languages, right? And regular language is the first one, first type of the language that we're gonna see. So these languages are not like the JavaScript or object-oriented programming languages, right? These are the formal languages. So these are basically set of strings. This is like the best explanation for them. Set of strings. Okay, guys, set of strings. And we're going to see the details, how we can build a regular language, what define a regular language, and what are their limitations and capabilities. Okay, guys. So let's start with the computational model first. So, guys, think about this thing as like the advancement in history. Like at first, we don't have like the modern computer that we have right in 1930s, 1920s, at the like the early of the 20th century. And then the scientists built those machines and they just add more power and they call it computer, right? But defining a computer is hard. Like, what's a computer? Like, is a laptop computer? Yes, we can say that. What about a thermostat? Or what about an oven? Right? They are computers or not? Tablets are computers and mobile phone are computers. But there are some other devices, like embedded devices, are they a computer or not? Defining what a computer is a hard task, and it is very controversial. Instead, we define computational model where your resources are changing. Okay, guys. So we're gonna see 3 computational models throughout this semester. And first we start with the finite state machines, finite automaton, and then the second one Poisson automaton, and the third one Turing machine. So with these 3 models, we're gonna see what languages that we can understand and what are the capabilities. Okay, guys. So each of these machines, each of these model has different features. They all have different features. Okay, guys. But let's start with a very simple model, which is called a finite automaton. Okay, guys. And in this model, the thing is we have extremely limited memory. Don't forget that. We have extremely limited, that's why it's called finite automaton. Finite, limited, sonlu, not sonsuz. Okay, guys. And actually, in our modern life, we are seeing those finite automaton in everywhere. Like for example, the door, the automatic door that opens when someone getting close to it, right? So just think about this system. Is this a computer? Can you say that a door has a sensor, right? These are the sensors. One and two, there are 2 sensors out there. And there are 2 sensors. And then there's a model who decides that if the door is going to be opened or closed, right? And how long you need to keep the door open is another problem. But this model should achieve those things, right? Should solve those problems. And to do that, we just have what do we like? So this model is a computer or not? That's a question, right? The computer or not? Can you call this model everything the computer? And so that's why we talk about this thing as like computational model, where you have a very extremely like limited memory. So what does this thing do? When someone on the front door, on the front path, right? The sensor sees that there's someone. So the door, if the door is closed, it opens, right? If someone on the front door, or front path, door must be open. And if the person goes through the door and stand on the rear path, then what? We expect that the door is going to be closed as well, right? But front and rear path, there are 2, like, this is somehow feel like the door is just one way. There is no like going this way, right? From rear to front. You guys, so how we can like model this problem? Okay, this is called like state diagram, as you can see. And here you can just build the system and tell the others how your system works by using this state diagram. When you look at that, we have 2 states, open and closed. States are used with these circles. These are states. Okay, guys, these are states. So for our door, we have only 2 states. Either the door is open or it's closed, right? So we just have 2 states. And then these are the arrows are our functions. Basically, what our sensors tell us, right? If someone is on the front door, and if door is open, we need to stay at open position. We don't go to close, right? If the door is open, no one is on the front or rear path. says neither, right? Neither of them sends you a signal, which means that neither front path or rear path has a person on it. So what we do? We go to closed state, close the door. We just send a signal, close the door. If when you're closed and someone on the front path, I'm sorry, I'm saying front door. When you're closed, the door is closed, someone is on the front path, what you need to do? You need to open the door and change your state to the open from the close. Okay, guys, if you look at that, it's a very simple state diagram. Tells you how you need to process the data that you receive or input that you receive, right? If your door is closed, as example, if your door is closed, if someone standing on the rear path, or both of them, or neither of them, you keep closed. Why both? Because maybe there's a chance to hit the door. I don't know like how the door is working. Maybe like, so this is the door, this is the front path, this is the back rear path. Maybe the door is like open this way. Right? So it's gonna hit the person on the rear path. So basically that depends on your requirements. But in this model, what we see is the door is closed and someone is standing on the rear path, we are still on the closed state. We don't do anything. If the door is open, someone is on the rear path, you keep open. Okay, guys. So I think like this is a very simple example. And how much data or how big memory we need to build such a mechanism? An idea like how big memory that we need to understand those stuff or to implement this automatic door. So we have two states, right? Two sensors. Each of them can say, so we have two sensors. We have two states, and each sensor can say is either 0 or 1. 0 means there is no one, I am not sensing anyone. 1 means there is someone standing on me, right? And the door has two states, is either open, let's say 1 is open, 0 is closed. Open is 1, 0 is closed, rear is, for the second one, it's going to be 1, both is 1, 1, right? So 0 is 0, 1, both is 1, 1, neither is 0, 0. Front is 1, 0. Is that clear? Both is 1, 1. So how big memory did we need to run this system? And the answer is not just 1 bit, right? Because like you have a door here, receives data from two sensors, and then your door basically decides it has just 1 bit memory. It's either 1 or 0. So it's open or closed. And then based on those inputs and based on the states, it computes something, it decides whether the door should be opened or closed, right? We just need 1 bit memory and like the input receivers and the output. The decider is there. Okay, guys, this is a very simple memory. This is a very simple system. We don't do states and like 2 inputs and 1 output. And this is the model that we're talking about right now. This is one of the simplest models that we're going to talk about. Okay, guys? So you can see that the table from here, like how the door acts based on the inputs. So the state is closed, neither of them giving signal, you stay close. If state is open, state is closed, someone is on the front door, front path, you open the door. You are closed, someone is closed, someone is on the rear path, you are closed. For both of them, you are still keep closed. So basically implement this thing. In embedded system, implement this thing, you just code this state diagrams, this chart to the embedded system, the chip, then you just install the chip to the system, then you're good to go. And what you need to do, what you need to have is just 1-bit memory to remember what state are you on right now. Because like you just need to remember if it is open or closed. Nothing else that you need to remember. And based on the data, you decide what you need to do. Okay, a single bit of memory is good too. So what about an elevator controller? Let's say you need to build an elevator controller that has 15 floors. Right? So right now, your state is different. Your states are different, right? Because like you're gonna have, if there's 15 floor, let's say starting from the 0 to 15, right? You have 16 different states. 16 different states. And what are the inputs? It's like just think about a typical elevator. There should be a button for each floor, right? From 0 to 15, there should be a button. And there are buttons outside of the elevator to call buttons, right? And then you need to know if you are carrying a person. You need to know that? I don't think so. It's not your concern. Last thing is that you need to know if the door is open or like safely closed or not closed. You just need to know this stuff. So you're getting complicated, right? Things getting complex here than just having this door example that we have. States are getting higher. You have more states. You have more buttons. You have more input channel, right? So that your machine is getting complex here. So that, which means that you need to have a bigger memory, right? And your decider should be like more complex or complexier than previous example. Okay, guys, that's all based on your requirements and what you're gonna want to build. Okay, guys. So how we can generalize this approach? How we can just build or define a state diagram that has like a type of the state diagram that is valid for all of this kind of stuff, all of the kind of finite automata. Okay, guys. So we have this shapes or we have this diagram, and we are using this diagram for all. Not like it is this diagram, like the arrows, the notation is like that. Okay, guys. So in this notation, what you're going to see is there are 3 states. What you're seeing is there are 3 states, Q1, Q2, Q3, right? And each state has an arrow coming and going out. And one of them has 2 circles, one of them has starting arrow. So guys, the idea of this like diagram is that this diagram shows that what your automaton acts based on the input. Okay, guys. So this is the start state. Depicted with an arrow coming from nowhere. This is your start state. And state that has 2 circles is called accept state. Okay, guys. Which means that your state diagram or your automaton accepts input that takes your state from the start state and ends up with an accept state. And the arrows are called transitions. What does it mean? So let's say this is our automaton, this is our system, and we have received an input which is 0, 1. So what we're gonna do? We are on the Q1, right? We start with the Q1, so we are just waiting here. The first bit is 0. The first bit of our input is 0. So what we do? 0 takes from Q1 to Q1. So we stay on the Q1. We don't change our state. There's nothing different, right? And then our second bit is 1. So 1 takes us from Q1 to Q2. Our input ends. We are on Q2, so we say that this state diagram, this file automaton accepts 0 and 1. Okay, guys. This is actually from. I think we should have more example and like explain what's going on there. I'm going to discuss all of this stuff, but is that clear, guys? How we just use the state diagram to read the input? So what if we have 1, 1, and 0? Let's look at this one. So 1, 1, 0. Again, we use the start symbol and we wait on Q1 at the beginning. And our first bit is 1, and 1 takes us from Q1. Takes us from Q1 to Q2. The first input is digest. We can remove it. And second input is 1. Right? If you're on Q1 and you receive a 1, then you stay on Q1. You don't change your state. And the third input is 0. So 0 takes you from Q1 to Q3. So you stay on the Q3. Okay, guys. So if you're on Q3, then this input ends here. You're on Q3, which means that the input is not valid for this diagram. Or you say that this diagram, this file automaton, doesn't accept 1, 1, 0. There's something wrong with this input. Okay, guys. So you can think about this like the elevator. Like let's say you have only 2 floors. Floor 0 and floor 1. You have only 2 floors. Okay, guys. If the elevator is on the first floor 0, let's say, if the elevator is on floor 0, and then there should be a valid input for this stuff. When you are close, someone press the button, they can press only the call button, right? If no one is on there, no one's on the elevator, there should be no, like the only valid input is the call button. There should be no other button. If your elevator somehow receives, let's say, there's a button like this thing, right? Close the door button. The door is already closed, no one inside. If somebody, like if you are receiving this kind of input coming from this close button, there's something wrong, right? So how we can differentiate the wrong input with the valid input like this? The input that ends up with a not accept state are not valid. Okay, guys, they have their mistakes. Okay, guys. So based on your automaton, based on your system, you build a different automaton, and we're going to see some examples. Is there a question about like the state diagrams and automaton, guys? So we just have received one input, and we just process the input, and we expect that the input should be end up with the accept state. All the others are not valid input for our automaton. Okay, guys. I think there's no question. So, an example for the input 1101. Okay, guys. So let's follow the step. First one, we start in the Q1, our start state. We're gonna read one makes us transition from Q1 to Q2. We are on Q2, so we are done with the first one. The second one is here. We take this transition. I think change here. We are stay on Q2. The third input is 0. Takes us from Q2 to Q3. And then the last bit is 1, and 1 takes us here. So this comma, like 0, 1 means either 0 or 1. Okay, guys? Either 0 or 1. When you read those definitions, the final thing is we end up with the Q2 so that we accept this input. Okay, guys, our automaton M1, in the book it's called M1, guys, it's automaton, accept 1101. Okay, guys. So let's say you be such an automaton, you have a system, but there are more than one ways to draw its automaton, right? What if you just draw it like this? Like this is Q1, so this is Q2, there's two circles, and this is Q3. So you can draw it like this. And like all the arrows, you can just set the transitions. Or you can just set it differently, right? So, or you can just have not 0, 1 like this, or 0 is different, 1 is different. There are two arrows for the Q3. So this state diagram has no standards. So that to have a standard, we need to have a formal definition to provide notation. Okay, guys, formal definition is necessary because like diagrams are, okay, they are very good to show, demonstrate what we have as an automaton, but they don't have any standard. We need to be more precise to express ourselves, especially in mathematics, especially in this kind of stuff. You have to say everything must be well understood by the others. Whatever you say should be like valid for everybody. That's why we rely on the mathematical definition, formal definition of this automaton. So guys, so far what we have states, we have transitions or rules, we have inputs, right, 0 and 1, we have a start state, and we have accept state. So we have 5 components of an automaton. By using this 5 components, we built the formal definition for the automaton. Okay, guys. So how we define automaton? Basically, what is a 5 tuple. So 5 tuple means that a sequence that has 5 items in it, right? And these are our items. There are 5 items: Q, sigma, delta, Q0, and F0. F. Okay, guys. Here Q is the finite set called the set. So this is set, not a sequence. So finite set called states. Then finite set called the alphabet, or input alphabet. In our case, it was 0 and 1, right? The delta is the transition function. Basically, this is our delta, right? This state is a function, right? It's a demonstration of a function. So this is a transition function. Gives you all details that you need to know, right? Delta is transition function. Q0 must be element of this Q, and it must be given to us as a start state. Right? We should have one start state. Okay, guys? And now we have F, the subset of Q. In this case, a set of accept states, which means we can only have one I don't know what to say about it. So we just only have one Q0, right? And then we have a set of accepts that we can have a set of accepts that we can have one or more accept state. Or we don't even have an accept state as well. The accept state, the F, can be empty as well. As a set is empty, right? Can be empty. Let's look at this automaton again. As you can see, we have 3 states. So our Q is Q1, Q2, and Q3. So we are just trying to formally describe, giving the formal definition of this automaton. Okay, guys? In this automaton, the set of states are Q1, Q2, and Q3. We have 3 states, Q1, Q2, and Q3. It's a set. We can give any order, right? The sigma is our alphabet, right? Input alphabet. It contains only 2 digits, 2 symbols, 0 and 1, right? So the set of alphabet is 0 and 1. And this is our transition function delta. right? Basically, you are giving on what state, based on what input, what transition you need to take. If you're on Q1, you receive a 0, you stay on Q1. If you are on Q1, you receive a 1 or you read a 1, you go to Q2. From Q2, 0 takes you Q3, 1 takes you Q2. From Q3, 0 takes you Q2, 1 takes you to Q2. Okay, guys? This is basically the how we define the function. And then we define a start state by giving here as a Q1, which is element of Q, right? Q1 must be inside of this Q set, the state set, the set of states, right? And then finally, we have F, accept states, and we just have Q2 here because we demonstrate the final state or accept state, the two circle. Okay, guys? So if I give you this, or if I give you this, no matter how we draw the state diagram, we know that we're going to talk about the same diagram, same automaton, because everything is formal here. Right? Anybody who knows how to read those data end up with the same automaton. There is no space for mistakes. But with the state diagram, if you just give the state diagram, not everything is so clear. Right? Not everything is so clear. People may get confused about this, can have interpret this thing different way. So that's why we rely on the formal definition, and this is the way of doing it. So let me repeat this thing again one more time. A formal definition consists of or has 5 items, so which makes it a 5 tuple, which is a sequence, right? So the order is also the order is also there. We can't change the order because it's a sequence. We know it's sequence because of this parenthesis, right? And in this formal definition, we have 5 items. The formal definition of 5 tuple is a 5 tuple. Starting with the Q, the set of states. Second one is the alphabet, which is your input symbols, set of your input symbols. In this case, we have only 0 and 1. And then your transition function is here. And then you have Q1 as a start state, showed or demonstrated with this arrow coming from nowhere. And then the final stuff is the accept state or set of accept states. Sorry, it can be more than there can be more than 1 or 0. And then you depict it with the 2 circles. Okay, guys, this is how you define your automaton formally. Because it doesn't. There is no room for that. Question is why F doesn't have Q3? It doesn't have to. It can, any state can be a final state. This is how you define how you build your automaton. So I can have something like that here, like Q4. This is also 0, 1, right? And then it's good to go. I don't need to change anything, right? Only Q2 can be the accept state. Okay, guys? You don't have to, Q2 is the highest value, so it doesn't have to be the accept state. There is no such a relation. So accept state is basically your automaton except set of strings. Not all strings are accepted by your automaton. Okay, and to show what state is accepted, you need to use this draw 2 circles. So a good example is something like that. The elevator example. Let's say you have not elevator, but let me do this car wash example. Okay, we have the car wash. We have a car wash machine, and this machine has 3 states. The first state is you just need to use water to like to all of the car. Then you have to apply foam to car, and then you have to rinse the car and then dry, let's say. There are 4 steps, right? The customer comes here and say that I want to get all the stuff. So I want 1, 1, 1, 1, and then you provide this 1, 1 to your automaton. Your car goes through your car wash system and get out. I think I made it. Okay, guys, so we have the car wash, right? And rinse and dry is okay. There are 2 accept steps. But the foam is not acceptable, or just water is not acceptable. If your customer says that I just have 1, 1, which means I just have water and foam, let's say they are the zeros, and you end up in the foam state, you can't stop it here. This is not a valid 1, 1, 0, is not a valid state for you, right? You have to be at least rinse and dry. Otherwise, you cannot leave a car with only foam. You can't allow a driver to pick on the water and foam, right? Is it clear? Like, so if you just say the water is Q1, or like welcome, like there's let's say welcome, the beginning state, you are here. Q1 is here, Q0 is here. You just on the front pad of like this water, the car washing system. Q1 is water, Q2 is foam, Q3 is rinse, Q4 is dry, right? So Q2 and Q1 are just not accept states. They are not valid. You cannot end up with this stuff. If your system are receiving an input call, let's say just these are the ones. Let's see, let me draw this thing again. All of them are just 1, right? And 0, you just skip it. So if you receive 1, 1, then you end up on the Q2, which is not acceptable. Something wrong with it. So you cannot accept the input, so your machine doesn't work. Your machine can't work with this stuff. Is that clear? What I mean by like accept state? But that depends on the system, of course. In this system, for example, so what kind of, do I have an example here? No, it is, so you building this system, right? Your system should work for your necessity. It is not something from the pick up the graph. There is no graph, by the way. And we have to define that this is how it's defined. I am not saying that Q2 is going to be the start state. It's given to me like this. In this example, your developer says that Q3 and Q4 are the accept states. If you're receiving an input that ends up with Q2, there's something wrong. You cannot run it. The system doesn't work with that. You're protecting yourself. If you receive 1, 1, 1, a customer comes in, put the system like say 1, 1, and 1, then I'm gonna do 0. Let's all the zeros are there. Then you accept it. Okay, guys. But this is just the Carver's example is very realistic. What we're going to do is like not that kind of concrete example. They're going to be abstract. For example, this language is, or the input of this state is all strings that must be end up with 1 or 1 that end up with, or ends with a 1 . So this must be ended with the 1 or okay, it has double 0 and with double 1 or double 0. Okay, guys. So this is the rule for this the automata. So let's look at some example. Let me clear everything. Oh my God. So let's see what we can accept and what we don't accept. So let's say our input is 0. What do we do? Start on Q1, still on Q1, doesn't accept. So 0 is not valid for us. What about 1? We are on Q1, we go on Q2, so 1 is okay. What about 0, 0? Right? 0, 0, 2 zeros still on Q1, don't accept it. My definition might be wrong. There must be at least 1, 1. And then the next thing is 1, 0, 1, let's say. 0, 1 is accepted because 0 and 1, right? Accepted. What about 0, 0, 0? You will only Q1, so it's not accepted. 0, 0, 1, it's not accepted because 2 zeros we see on Q1, 1 takes to 2, it's accepted. 0, 1, 0, 0, 1, 0, not accepted. You follow it, right, guys? 0, 1, 0, not accepted. And now we have 0, 1, 1. So this is 0, 1, and 1 accepted. Now 1, 0, 0, 1, 0, 0 accepted. 1, 0, 1, 1, 0, 1 accepted. And then what? 1, this is the 1, 1, 0 and 1, 1, 1. Right? So 1, 1, 0 not accepted. 1, 1, 1 accepted. So you see some of the strings are accepted, some of them are not. And there's a rule, right? And the rule, I think, says that it's going to end up with the 1. It contains at least 1, 1. And end up with 2 zeros. Okay, guys? So end up with 2 zeros, right? That's what I'm saying. Or double, or the end up with the even number amount of zeros. Might be better explanation. Because just 0, 0, you just have 2 zeros, even number of zeros. This must be the rule. So 1, 0, 0 doesn't work. Like 1, 0, 0, 0, 0 working, all zeros doesn't work, or 0, 0, 1, 0, 0 working. So you have to have at least 1, 1. Or if we just say that there is no 0 is also even, right? We just can say that the number of the 0 at the end must be even and it contains at least 1, 1. So this is the actual answer. There must be at least 1, 1, and then number of zeros must be even. Is that clear, guys? There must be at least 1, 1 because of here. And there can be any other ones, all 0, 1, it doesn't matter. But the n must be 2 zeros. Or again, like at the end 0, 1 is accepted. Okay, this is the rule. So we're going to see so many like examples. And each of the examples gives us like how we can build automata or how we can read them. So guys, if A is the set of all strings that M accepts, like this, right? Here we have the L of this automaton language, right? We have 1, right? 1, 0, 1, 1, 0, 0, right? What else we have? 1, 1, 0, 1, 1, 0, 0, 1, 1, also accepted. 1, 0, 1, 0, 0, like goes on, like all the rules that we just defined, right? So if A is the set of all strings that M accepts, we say that the set of all strings A is the language of machine M. Okay, guys, this is the definition of this is how we show it. L of M is A, and M recognizes A or M accepts A. This is what we say. Okay, guys. So, but A is the set of all strings that M accepts. Let me draw a down simple automaton. Okay, guys, this is Q0, this is Q1. So this is 0. This is 0, this is 1, and then this is 0, 1. Okay, guys. So this automaton accepts all the strings that has at least 1, 1. Right? If you just say 1, 1, one amount of 1, then this one takes you from Q0 to Q1, and then with all the 0 ones, you stay on Q1, so it doesn't change the state. If you just, no matter how many zeros that you have, you only need to 1, 1, then you're good to go. So this is basically all the strings that has like alternate you can bit minus 0, 0, 0, 0, 0, 0, right? 4 zeros, 5 zeros goes on. Everything that you can build minus those stuff, all the zeros. So the string the set is called the language of the machine. Okay, guys, and we say M recognizes A or M accepts A. Okay, guys. So if you want, let's take a break. 10 minutes. This is 51. Make it 15. So we're gonna be here on 2:05.